Okay, let me welcome all of you back for another organic chemistry session. We do have a lot of material to cover today. We are going to finish on chapter 20, and then I will start with chapter 21. Okay. One announcement to make. Our homework assignment for this week has been posted, and the due date is Sunday, March 30, that's March 30 at 11 p.m. Also, I have posted a chapter 21 hour for spring 2013 at the review session for that assignment. I posted in Blackboard and also in YouTube. So for those of you who want to take advantage of it. Okay, before we start on finishing on chapter 20 and then going to chapter 21, I'm sure you guys want us to go over the quiz questions. Okay. Okay, Chad, can you go ahead and read this for us? Okay, thank you. Okay, this question here, of course, this question is simply testing your knowledge of reagents. Okay, so I'm assuming that all of you know your reagents by now. So anyway, we have a series of reactions, and all you have to do is provide the reagents for each transformation. So let us take a look at this one here. We want to go from benzene to toluene or methylbenzene. And keep in mind that in this sequence of reactions, all we want to do is to prepare a carboxylic acid. Okay? So, okay, what do we do going from benzene to toluene or methylbenzene? What reagent do we need here? Alkylation, the Friedel-Crafts alkylation, okay. Okay, so for Friedel-Crafts alkylation, in this case you need methyl chloride in the presence of aluminum chloride. Okay. How about B? We want to go from the toluene to nitrotoluene. We want to introduce the nitro group in the para position. Nitration, very good. Nitric acid in the presence of sulfuric acid. Okay, now we want to go from the nitrotoluene to nitrobenzoic acid. In other words, we want to transform the methyl group, which is attached to benzene, to the carboxyl group. Okay, what's the reagent? Potassium permanganate? Okay, very good, excellent. Do this in the presence of dilute acid. Okay, and last on this series of sequence of reactions, we now want to go from the nitrobenzoic acid. What we want to do now is to reduce the nitro group to the amino group. So what do we need? Iron. What is? Iron. Okay, iron with what? Hydrogen. Okay, very good. We use iron with acid, HCl. Okay, Cinda, can you read this for us?
Yes. Write the missing reagents for the following sequence of reactions. Okay,
thank you. Okay, once again, this is also testing your knowledge of reagents. Keep in mind, you need to know your reagents before you can't do anything in organic chemistry. Okay, so that is why we would like to test your knowledge of reagents before we ask you to do anything else. Okay, now we want to go from this molecule here. We want to introduce a bromine in the into the benzene ring. What reagent do we need here? What is it? Br3, Br2. Okay, bromine with what? Iron 3 bromide. Okay. Okay. How about here? Now we want to go from this here. These are bromobenzene molecule forming a Grignard reagent. What do we need? Magnesium? Okay, very good. Magnesium, if you want to put the ether in there as a solvent, that is fine. Okay, so now we have the Grignard reagent. We now want to form a primary alcohol. Go from a Grignard reagent to a primary alcohol. So what do we need here? Aldehyde. Okay, in this case, what type of aldehyde? Formaldehyde. Okay, very good. So what we do here, since we already have the Grignard here, so we simply just place the aldehyde here, 1. Formaldehyde, and then step 2 will be the hydronium ion. Okay, okay, that will take the Grignard will react with formaldehyde to give you a primary alcohol. Now, supposing you have a secondary alcohol with Grignard, what kind? Secondary. You want to make a secondary alcohol with Grignard. What kind of molecule do you need? An aldehyde, a regular aldehyde, right? Okay, very good. In other words, if you have a Grignard reagent and you want to form a secondary alcohol, use a regular aldehyde, not formaldehyde. Okay, very good. Okay, now we want to go from the primary alcohol to an aldehyde. So what reagent do we need here? Okay, desmartin, very good. Sometimes desmartin is fine, but sometimes your book will refer to this as iodine. So let us make sure you have everything in there just in case. Okay, you could have desmartin. Sometimes your book refers to this as iodine. Okay, so keep that in mind. Okay, or what other reagent can we use here? PCC, okay, or PCC, okay. So desmartin or PCC, each one of those will transform a primary alcohol to an aldehyde. About here, now we want to go from this aldehyde. We want to introduce the chlorine into the benzene ring, which will be, of course, it's going to be metal to the formaldehyde group. So what reagent do we need here? Chlorine with iron 3 chloride. Okay, very good. Okay. Now we want to go from this aldehyde here. We want to form a cyanohydrin. What reagent do we need here for here? HCN? Okay, very good. Hydrogen cyanide will add to an aldehyde to give you cyanohydrin. Okay. Now we want to go from the cyanohydrin. We have an hydroxy group here, and then you have the nitride here. We want to go to carboxylic acid. At the same time, we also want to maintain the hydroxy group. So what reagent do we need here? Hydronium ion? Which one? The hydroxide? Well, in this case, yeah, you could use any one of those. In this case, it does not matter. I'll tell you why. You could use hydronium ion. Okay? I'll tell you why. You could also use or hydroxide, step 1, followed by hydronium ion. Let me tell you why I say you could use the hydronium ion. You see, this here, the hydroxy group, right? This hydroxy group has no chance of dehydration because there is no hydrogen here. Okay, the reason why you normally want to use a basic hydrolysis to transform a nitrite to a carboxylic acid is because you do not want the hydroxy group to be dehydrated. Since there is no hydrogen here, then you don't have that problem. So in this case, we could actually use the hydronium ion. Okay, you follow that? Okay. Now we want to go from the from this alpha hydroxy acid to the chlorinated molecule here, and at the same time we are going to form an acid chloride. Okay, so what reagent do we need? Thionyl chloride. Very good, very good. Thionyl chloride, if you recall, will transform an hydroxy group to replace the hydroxy group with a chlorine atom. It will also take a carboxylic acid and give you what we call an acid chloride, okay? And that is what we have here. So, finally, this step here, now we want to hydrolyze the acid chloride to carboxylic acid. What do you need? Okay. Well, in this case, just water. Just use plain water. Okay. Water will hydrolyze take water here, or dilute acid if you want. We'll hydrolyze the let's use dilute acid. We'll hydrolyze the acid chloride to carboxylic acid. Okay, so here you could simply just have water or dilute acid. Okay? Yes. Yes, each one of these is 1 point. Okay, so if you get everything right, you get 19 out of 12. So, okay. Okay, Alexis, can you read this for us? Okay, thank you. Okay, here, once again, just checking your knowledge of reagents. So, filling the missing reagents, okay? At this point, we want to go from a terminal alkane to a primary alcohol. So what reagent do we need here? Boration, oxidation, right? Okay, very good. So here, borane, and then you follow that up with hydrogen peroxide in basic medium. Okay. This will be an anti-Markovnikov addition. Addition of water. We know that is what that reagent does. To add to a hydrogen and hydroxyl group across the carbon-carbon double bond in an anti-Markovnikov fashion. Okay. In this case, anti-Markovnikov simply means that the hydrogen goes to the carbon that has less hydrogen, so the hydrogen goes here, okay, and then the hydroxyl goes to the other carbon. Okay, so now we want to go from a primary alcohol to a primary alkyl bromide. What reagent do we need? PBr3, okay? Very good. Okay, so now we want to go from the alkyl bromide to a nitride. Okay, what do we need for that? HCN. Okay, here you use either sodium nitride or sodium cyanide or potassium cyanide. Okay, very good. Okay, this will be an SN2 type reaction in which the cyanide will act as a nucleophile to displace the bromine from this carbon here. Okay, so you get the nitride. Okay, now we want to go from nitride to a carboxylic acid. What reagent do we need? Hydronium ion? Right? Very good. Okay, and then we have this here going from carboxylic acid to a primary alcohol. What reagent do we need for this? Which one? LAH, very good. LAH, followed by, okay, I will also give you one new reagent for this. You could also use BH3, so that's another thing for BH3 you need to make, keep in your reagent list. BH3 followed by hydrogen peroxide. This will also reduce a carboxylic acid to a primary alcohol. So right now you have two reagents that you could use for that purpose. So make sure you make a note of that. Okay, finally we're going from a primary alcohol to an aldehyde. What reagent do we need? You all know that already, right? Okay, either pyridine, right? Or you may call it desmartin. Or what other reagent? Or PCC? So folks, you see here, the first thing you need to do in order for you to understand organic chemistry or to do organic chemistry, you need to know those reagents. Okay, so when you come to me, you say, I studied so hard, then I give you, what reagent do you need to go from here to here? You're looking at me like, what is that? Then I say you have not studied. Because that is pure memorization. You don't need anybody to show you how to do that. Okay? You could pick up a book and do that. You don't even need me to do that. So anyway, the first thing you need to do, you need to know those reagents. It's a lot of work, but there is no way around it. Like I keep telling you, those reagents are the ABC of organic chemistry. Okay, so now let us now go to, I'll finish up on chapter 20. Okay, on chapter 20, I believe we covered just about everything, but there is one more topic I would like to discuss with you before we leave today, and that is spectroscopy, as some aspect of spectroscopy, since we are getting close to the end of the semester. So I want to give you an opportunity to refresh your memory with regard to spectroscopy. But before we do that, let us do a couple more problems. Let's do a couple more problems. Okay, Victoria Lashin, can you read this for us? Okay, thank you. What I want you to do, starting from butanoic acid, provide synthetic scheme for butane nitride. Okay, this is, I believe we did this before, so we don't really, this is fairly easy to do. So we are going to only do the first one. Okay, butanoic acid, of course, is this here. We want to go from butanoic acid to make butane nitride, which is this. Okay? What do you think we need to do here? If you take a look at the problem here, we are going from this molecule here, butanoic acid contains 4 carbon atoms, and of course the butane nitride also contains 4 carbon atoms. Okay, how do we approach this? Yes. Okay. Okay. You want to reduce the carboxylic acid? Okay. You want to turn into a primary alcohol, we could use the reagent I just given you, BH3, followed by hydrogen peroxide. And so that will give you a primary alcohol. Now, what do you do with that? PBr3? Okay. Okay, let's see. PBr3. So you want to replace the hydroxy with bromine. Okay, so far, well, I'm not saying so far so good, but that's okay. Okay, now what do you do from there? You want to do an SN2 reaction with... Okay. But if you do that, you are going to get pentane nitride.
Right. So we answer now.
Right? Okay, if you do this here, what you will get will be pentane nitride. But we want butane nitride. Pentane nitride has 5 carbon atoms, yes. Oh, I thought you were raising your hand. Okay, so what do we... No, the point is here, you need to lose a carbon atom to do this. Okay, it's not as innocent, the question is not as innocent as it seems. So that is why you have to think. This is where you now require that you think critically. Okay? Yeah, this is beyond reagents now, yes. Okay. Okay, very good, excellent. Okay, in other words, you want to form an alkene and then cleave the alkene with excellent, excellent. You see, but you need to know those reagents before you could then think critically. Okay, very good. So what do we need to do here? Just Alexis gave us. Okay, so yeah, we do all of this here. Yeah, we could still do all of this. And then once we get to here, now you want to take this and you want to transform this to potassium permanganate, potassium hydroxide. In other words, you want to form a carbon-carbon double bond. Okay, so now you have this. And once you do that, once you form your alkene, now you want to take that here with potassium permanganate. Okay, that will cleave this here. I will clip this. Now you are going to get this propanoic acid. Oh, this other carbon becomes carbon dioxide. Now, once you get your propanoic acid, now you now go through the sequence that you guys gave me earlier, which means that you now do your reduce the carboxylic acid. You could use LAH or borane if you want. Then followed by hydronium ion. So now you form this. And then once you do that, then you do the PBr3. Okay? You can see here, you have to think through this. But before you can do that, you need to know those reagents. Without knowing the reagent, there is no way you can do this. So anyway. So now you form the bromide. So at this point, you now take the take this here. You can now react with the sodium cyanide, and then you get your butane nitride. But the first thing that should come to your mind is when you do the analysis of the problem, say, wait a minute, it looks to me that I have to lose a carbon atom. Then that should trigger something in your mind. How do I lose a carbon atom? Okay, double bond, potassium permanganate, those kind of stuff. Okay? Okay, so let us try the next one. Oh, you want me to go back? Yes.
Could you have dehydrated?
Huh?
Could you have dehydrated
The OH?
Yes.
Yeah, the primary alcohols are very difficult to dehydration. Is I guess theoretically yes, you could do that. Give some credit for that, but primary alcohol generally are very hard to do dehydration on. Okay. Okay, can I move on? Yes. Huh? That will give you the aldehyde.
Right.
Yes. That will give you the aldehyde. But then yes, then you could reduce it to with LAA2 and primary alcohol. And that will be okay. Okay. Now let's do a spectroscopy problem before we leave this. Okay. Okay, Kiara Wallace, can you read this for us?
Structure of a compound C5H7 and also that exhibits anywhere of absorption at 1735 and 2550 at the following H in the mark spectrum. Okay,
thank you. Now, I brought this up so that you guys do not forget your spectroscopy. Remember we did spectroscopy last semester. Now, we have this problem here. They have given you the proton NMR spectrum for this compound. The formula is C5H7, 1 nitrogen, 2 oxygen atom. And then they've also told us that that molecule has an infrared absorption at 1735 wave number, and another infrared absorption at 2250 wave number. Do you know what kind of information those two will give you, the infrared data? Okay. So anytime you see 1735 wave number in infrared spectrum, what that tells you is that you have an ester. You have an ester. Okay, so right away you know that you have this type of functionality in the molecule. Okay, so you have an ester. And then Anytime you also see some any absorption around 2200, 2250, what that tells you is that either you have a carbon-nitrogen triple bond or a carbon-carbon triple bond. Okay? So in this case, let us make an assumption, since we have nitrogen here, that we have carbon-nitrogen triple bond. So the infrared spectrum has already told us that we have an ester. It has also told us that we have a nitrile. Okay. Now the formula is this here. Now if we do the index of hydrogen deficiency for this, for those of you who are not in my class last semester, let me give you the formula here. Index of hydrogen deficiency which you call IHD. The index of hydrogen deficiency will tell you the number of multiple bonds or rings that you have in your molecule. For each index of hydrogen deficiency, it is a double bond or a ring. Now, if you work this out, the formula for index of hydrogen deficiency is carbon minus, clear this here. Okay, just to refresh your mind, IHD formula equals to the number of carbon in the molecule, number of hydrogen atom divided by 2, number of halogen divided by 2, number of nitrogen divided by 2 plus 1. Now, if you do all of this, of course, in this particular instance here, since we have 5 carbon here, 5, and 7 hydrogen, so that is minus 3.5. We don't need to worry about the halogen, so that doesn't factor into the equation at this point. And you have 1 nitrogen, so that is plus 0.5. Then plus 1. If you work that out, that gives you an index of hydrogen deficiency of 3. Okay, so what does that tell you? We've already told you that you have triple bond, you have carbon-oxygen double bond, right? Those are all your index of hydrogen deficiency. The triple bond is 2, and then this carbon-oxygen double bond is 1. So those are all of your sites of unsaturation right there. So now let us see if we can work this problem. Now, if you recall what I told you last semester, when you have a spectrum like this, the first thing you want to do, write the data out in a tabular form. Okay, so let us take a look at this data. We know TMS, this is the internal standard. We don't need to worry about that. We have a peak at 1.3. Oh, by the way, I will tell you that this number of hydrogen here is 3. That will help you out. This is the integration line. And number of hydrogen here responsible for this signal is 2. And number responsible for this here is also 2. So that will account for all of the 7 hydrogens. 3, 2, and 2. Okay. So we have a peak at 1.3, say about 1.3 parts per million. And that is a triplet. If you look at it very carefully, that's a triplet. And then we have another peak at about 3.5. And that is a singlet. And then a peak at 4.3, and that is a quartet. Okay? In essence, this molecule only has 3 types of hydrogen. That is what this is also telling you. You only have 3 types of signals here. Okay. Let us now begin to put the pieces together. You see a peak? Okay, by the way, this is 3 hydrogen. Sorry, this is triplet. This is 3 hydrogen. This is 2 hydrogen. And this one is 2 hydrogen. Okay, let's put the pieces together. Let's look at the most obvious information here. 4.3 quartet. What does that tell you? 2 hydrogen. What does that tell you? Don't forget your M+2 rule. I'm sorry, yeah, M+1 rule. M+1 rule. In other words, a given set of hydrogen will be split into M+1 peaks. Okay? And the N is the number of hydrogen that it sees. In other words, if I have this, say I have this here. If I have this here, the signal for this hydrogen here will be split into M+1 peaks. The N is the number of hydrogen that this one is seeing, which is meaning that what is next to it. So therefore, this will be a triplet because it is only seeing 3 hydrogen. Okay. On the other hand, if you take a look at this set of hydrogens here, how many hydrogens are they seeing? They're seeing 5. So therefore, this will be split into a sextet. 6. N+1 is 6 because it is seeing 5 plus 1 is 6. Therefore, about this one here, what will be the multiplicity of this hydrogen here? How many hydrogen are they seeing? They're seeing 2 because only 2 hydrogen are next to it. So this will be a triplet. Okay? Okay, so let us use that same set of rules to determine what the structure of this molecule is here. Take this out. Okay, so the most obvious information here, a quartet, 2 hydrogen. 2 hydrogen, that is a quartet. What does that tell you? It is next to a methyl group, exactly. So you must have this. That is what that is telling you. CH2. In other words, on this side of the molecule here, there should be no carbon that contains hydrogen on this side of the molecule. Because this is now, this is now showing you a quartet because it is seeing these 3 hydrogens here. So therefore, we must have this. You follow that? Okay. Now, let us see what will complement this here. We have 1.3 triplet, 3 hydrogen. They complement each other, don't they? Okay. Okay. So we have an ethyl group in this molecule. We have a cyano group in this molecule. We have an ester in this molecule. So all we need to do now is put the pieces together, right? Because all we need to explain now is this singlet 2 hydrogens. So let us put the pieces together. So what you do when you have this kind of problem, based on the information that you are given, based on the data, you begin to put all your pieces, determine what those data will tell you, and then using the data to construct your structure. Okay, so we have this. I would say we have this here, CH3, CH2, and you notice here, this CH2 here, that is 4.3. For this to be 4.3, that means it must be next to electron withdrawing group. Okay? And since you have an ester in this molecule, I would take a chance and say probably next to oxygen. Okay? If that is the case, therefore your carbonyl must be here. Because you have an ester. Okay? So now, this molecule only has 5 carbon atoms. So we only have 2 more carbon atoms to account for. we already know that we have a cyano group, right? And that has to be at the end of the molecule. So therefore, this has to be this here. So in this case, you are actually playing detective. Okay? Okay, so now does this match the data that we have? Okay, the formula is consistent, C5H7NO2. That is consistent. This formula is consistent with the formula that we have. Okay, now the other data we have, this methyl here, that is the one at 1.3, which is this here. The CH2 next to oxygen, that is the one at 4.3, which is this here. The CH2 here is a singlet. Okay, that means it does not see anything. N plus 1, where N is 0. It doesn't see anything. So therefore, that is consistent also. And that is the 3.5 here. Okay, consistent. It is next to carbonyl, also next to a nitrile. I think we account for everything here. So therefore, this is our molecule. Okay, do you have any question on this? Okay, so anyway, from now till the end of the semester, we are going to bring you a spectroscopy problem, so that will allow you to actually begin to refresh your memory on spectroscopy. Okay, now yes. If it's what, say that again? Oh, how do I know that this is 3? Yeah. Oh, okay, I see. Okay, very good question. Well, this integration here, actually, this is a ratio. If you look at this ratio, this line here, this right here, compared to this here, it's actually a ratio of the area under that peak. Okay, ordinarily, the instrument will measure that and give you the area. So to give you that ratio, then from there you'll be able to tell whether it is the relative number of hydrogen that you have. But you could also use a ruler. If you just gave you this, you could use a ruler to measure the distance. And then from there you determine the ratio. But for the most part, I will give you the number of hydrogen to save you some trouble. Okay? Now most tests that you will be given, the chances are they will give you the number of hydrogens. Okay, so now let us now go back and start with chapter 21. What time do we have? Okay, we still have plenty of time. Okay, at this point we want to start with chapter 21. You will find that chapter 21 is actually related to chapter 20. Of course, the title of this chapter is the chemistry of carboxylic acid derivatives. In other words, those compounds that are derived from carboxylic acid. Okay, for the most part, what I will do in this chapter here, I'm going to combine the synthesis and nomenclature, okay, rather than doing them separately. So I will combine the nomenclature and synthesis. And then we will discuss the reactions of the various carboxylic acid derivatives. More specifically, we are going to discuss nucleophilic acyl substitution reactions. Okay? Okay, on this slide, of course, you have a list of learning outcome objectives. You should use this as a study guide to prepare for the quizzes and exam for this chapter. Okay, so I'm going to leave that to you. So now we want to ask ourselves, what are carboxylic acid derivatives? The molecule on this slide showed you examples of those molecules that we refer to as carboxylic acid derivatives. Of course, you can see here, this is carboxylic acid itself. As you can see, most of these molecules are related to carboxylic acid. They could actually be derived from carboxylic acid. As you can see, if you take this carboxylic acid here, this part of the molecule, we call that a carbon attached to carbonyl. We refer to that as an acyl group. So we are going to be using that nomenclature throughout the rest of this semester. That is an acyl group. An acyl group is that in which you have a carbon atom or an alkyl group attached to a carbonyl. We call that an acyl group. For example, this would be an example of an acyl group. As you can see here, all of the carboxylic acid derivatives, they have that much in common. They all have the acyl group. Okay? Now we have what we call the acid chloride. In this case, an halogen, specifically fluorine or bromine, is attached to the acyl group. We call that the acid chloride. Then we have the acid anhydride. In this particular instance, we actually have two acyl groups joined to the same oxygen atom. We have two acyl groups joined to the same oxygen atom. So we refer to this as acid anhydride. And then we have the ester. Most of you have seen esters before. Okay, in this case, what have we done? The acyl group is simply now attached, is joined to an alkoxy group. Now our oxygen attached to some alkyl group. Okay, then we have the amide, in which case we now have the acyl group is attached to nitrogen atom, and that nitrogen atom could be attached to two hydrogen atoms or two additional carbon atoms. Okay, we call this type of compounds amide. Some people refer to this as amide. So that would be your choice what you call it, either amide or amide. And then we have the tau ester. The tau ester is an analog, the sulfur analog. Of the ester. You see here. So all we are doing here, replacing the oxygen with sulfur. So we say this is tau ester. And finally, we have the acyl phosphate. Okay, and we have the acyl group attached to phosphate molecule. Now, of all of these carboxylic acid derivatives, we are going to focus our attention on only 4 of them. Okay, as far as we are concerned in this class, we are going to focus on just 4 of these. And our focus will therefore be on the acid chloride, or acid halide, either acid chloride or acid bromide, ester, acid anhydride, and amide. Those are the 4 that will be of interest to us. So what I want to do at this point, I want to go straight to the synthesis of these compounds. Fortunately, some of them we've already synthesized before, so this will be reviewed to most of you guys. And so while I do the synthesis, I will also give you the nomenclature. So let us start with synthesis of carboxylic acid derivatives. So I am going to start with the acid halide. Specifically acid chloride. Of the acid halide, the acid chloride is probably the most useful, so that is where our focus will be. So if you take this we've done before, so this should not be new. You take a carboxylic acid. Of course, we take a thionyl chloride. We get okay, this molecule here we call this benzoic chloride. And now, how do we derive that name? To derive the name of the acid chloride or acid halide, what you do, you take a look. This name will be derived from the name of the corresponding carboxylic acid. In this case, the corresponding carboxylic acid, of course, is benzoic acid, this right here. That would be the corresponding carboxylic acid. So to derive the name of the acid chloride in this case, what you do, you remove the IC and the word acid, and you replace with YL and then the word chloride or bromide. Okay? Okay, so you replace with YL. So that is why we got benzoic chloride. Okay, if we have this molecule here, we take butanoic acid, and we react with thionyl chloride. Of course, we get this here. Okay, so this is butanoic acid. Okay, so what would be the name of this acid chloride here? What would be the name of this? Butanoic chloride. Very good. This would be butanoic. Now, supposing I have this one here. Okay, I take this acid here, and then of course I get this acid chloride. Okay, so we start with this here. What will be the name of this one here? This will be called benzoic acid, right? Okay, so that would be 3-chloro. That's 1, 2, 3, 4, 5. 3-chloro, 5-nitro benzoic acid. Right. 3-chloro, 5-nitro benzoic acid. Okay, so therefore, what will be the name of this acid chloride here. 3, exactly, 3-chloro. So this becomes 3-chloro, 3-chloro, 5-nitro, benzoyl chloride. Now, if you have an acid chloride in which you have the carbonyl attached to a cyclic system, this here, so this will be a slightly different from the rule that we've just given you. If you want to give the name of this here, what will be the name of this acid here? That will be cyclohexane carboxylic acid, right? One word. You take this, toluene chloride, in this case here, so this is a slight departure from what the rule that we've just given you. In this case here, what you do here, you give the name of the cyclic ring system, so this becomes cyclohexane. Then you give this here as carbonyl, okay, carbonyl. Then you have the word chloride. Okay, so that is fairly unique because that is not derived directly from the corresponding carboxylic acid. So in this case, anytime you have a ring system attached to the carbonyl, you give the name of the ring system, and then you add the word carbonyl, one word, and then chloride. Okay, so that is the only one synthesis of the acid chloride that you guys need to know. So at this point, let us go to the synthesis of the acid anhydride. Synthesis of acid anhydride. To synthesize the acid anhydride, we take, say for example, we could take this here, take acetic acid. You take acetic acid, and then we react this with a base. Sodium hydroxide or potassium hydroxide. So you are going to get an acid-base reaction here. And then you get this. You get what we call the carboxylate. Carboxylate coming from carboxylic acid. And then you now take this, of course sodium will be here somewhere. You now take this, you now take an acid chloride, okay, so you react the carboxylate with the acid chloride. What do you get? You get this. And then of course the sodium chloride here. So you are going to displace the chlorine that is attached to this carbonyl, yes. Yeah. No. Okay. So now we get the acid chloride. Now what will be the name of this acid chloride? Now to derive the name of any acid chloride, what you do, you take a look at the molecule. Okay, if you take a look at this side of the molecule, you say to yourself, the corresponding carboxylic acid will be acetic acid. Okay, and then also now you take a look at this side of the molecule also, the other side of the molecule. This here also, you say, well, the corresponding carboxylic acid will also be acetic acid. So therefore, what do we call this? So what we do, well, we simply say acetic anhydride. In other words, this comes from acetic acid. Acetic anhydride. Two separate words. Now, supposing we have a mixed anhydride. Supposing we have this. Take benzoic acid. Step 1. Step 1 will give us the carboxylate ion. And then step 2, you add any appropriate acid chloride. Okay, let us say we want to do this. Okay, so now what do we get? We get this. So we get this mixed anhydride. So what do we call this? Okay, you take a look at this. Okay, this part of the molecule here looks like it came from benzoic acid, right? Okay. Then you also now take a look at this here. So this part of the molecule also looks like it comes from acetic acid. Okay, so therefore, no. Oh no, I made that mistake. It should be, I'm missing 2 carbons here. Come from propanoic acid. Let me take this off. So it looks like this part is coming from propanoic acid. So what do we call this? Okay, you are going to give the name of the 2 acids. So this becomes benzoic in alphabetical. You give the name in alphabetical order. Becomes benzoic, propanoic, separate words, anhydride. So in the case of the mixed anhydride, you give the name of the corresponding carboxylic acid, and then you add the word anhydride. Okay, benzoic, propanoic, anhydride. Okay, so we've given you one method for making anhydride. Now this method here is actually used to make a lot of your pharmaceutical drugs that many of you are probably familiar with. So let us use this method here to make Tylenol. If you take a look at this here, oh no, I want to make aspirin. Tylenol will come later. Okay. If you take a look at that, oh, okay, I'm jumping down here. That's an ester. So I'll come back to that because that's an ester. Because right now we're making an anhydride, okay? I'll come back to that. Just excuse me for a minute. Anyway, so far we've given you one method for making an anhydride. So now let us go to the ester. synthesis of ester. Okay, and that is where the aspirin that I wanted to show you. Now, if you take this molecule here, okay, this is called salicylic acid. You could use this to make aspirin. If you just simply take this, and we take acetic anhydride, and also in the presence of catalytic amount of hydroxide, very small amount of hydroxide. What do we get? We get this here. We get aspirin. And that is acetyl salicylic acid. And that is your famous aspirin. It's actually very easy to make. If you want to give a demonstration to high school students, very easy. Just take acetic anhydride, take salicylic acid, just mix them together. You get a very nice crystalline powder right away. It's a very good demonstration if you want to do that. Anyway, so this is how you make aspirin, okay? And you make millions of dollars, you know, just selling. Okay. So anyway, with regard to the synthesis of esters, what do? You take an alcohol, you take an acid chloride, okay, you get an ester. Okay, another way of making an ester, to do an SN2 reaction, if you have, say for example, we have this. This time? So let me finish this and then we go. Another way of making an ester, if you take this here, sodium hydroxide, the sodium hydroxide will give you the carboxylate, and then you then alkylate that. Say you will then take methyl bromide or methyl iodide. So in this case, what you are going to do, you do an SN2 reaction, and that gives you and to name this name comes from the corresponding carboxylic acid. Carboxylic acid here is acetic acid. Okay, to name the ester, you remove the IC and the word acid, and you replace with ATE. Okay, so this becomes acetate, and then you give the name of the alkyl group that is attached to the oxygen. In this case, methyl. So this becomes methyl acetate. These are separate words. Okay, so first, when we come back on Thursday, we will continue with chapter 21. We'll continue with the synthesis of esters. So I will see you on Thursday.